So yeah, string theory. So string theory is basically I guess the like umbrella way to describe it is like if you were to take quantum theory and you were to take a general relativity, right? These are two very, very, very different things. One of them is quantum theory is the study of things at like incredibly small levels. Like, okay, if anyone's seen like Ant-Man and the Wasp, like Quantumania, the quantum realm, okay, so we're familiar with that. And the other side of that is general relativity. So that's like black holes, that's your really, really, really big space stuff. The problem is that these two theories do not work well together. If you try to apply quantum theory at like a general relativity scale, you basically will get infinite numbers. Like your formulas will essentially go to either infinity, or they would be try to like divide by 0, or it just basically doesn't work. You will reach a point of singularity. I am made of strings or called muscle fibers. You're made of more strings than that. Don't worry, we're gonna get into that. Almighty strings are bigger than mine. They're straight muscle, respectfully. But so the problem is that we don't have any way to relate these, because there's always gonna be like, if you try to apply general relativity to quantum, you get infinite, you know, you get singularity. Things don't work. We get black holes that basically shouldn't exist the way they do. Like the math just doesn't work out. And so what string theory is trying to do is it's essentially making a bridge between the two. Because if we can connect those two massive theories, we can essentially make what is called the theory of everything, which is explaining how everything works totally, like period. So is basically, the way I understand it is like, if you can understand, or more accurately, if you can control string theory, you are a deity, you're divine, because it affects literally everything that there is. So let's go ahead and kind of hop in here. So the difference between string theory and like modern physics is based on points, whereas string theory is based on strings. And what I'm saying here is that if you have like everything in modern physics is based on like a single point that you can calculate and go off of. The problem is that the single point doesn't actually relate. It is, yeah, I'm actually bugging down. It doesn't relate to gravity too well. So in physics, and I do some physics, like, you know, normally I have to be the ship engineer, you know, since it's just me right now. If you're trying to do gravity on a point, the math gets kind of weird. It doesn't really work out. So a lot of the times, like if you're doing it on a single instance, the gravity constant is just dropped. And you instead just act as though it's like, it doesn't apply. It's kind of like whenever you're doing velocities and you don't take into account air resistance. It's kind of like that. It's weird. The problem though is that doesn't really work, right? We need a way to be able to follow gravity to like see how it affects things over like a large scale. And the way that we do that is by using strings. So what strings are basically, let's go back to that engineer example. If you were to take that point and now we want to apply gravity to it. Well, if you try to apply gravity to a single point, it's not gonna work. So what we can do is we can actually expand that point out and to where we can apply gravity over a series of points, or a air quote string, to get that gravity constant in there. And the cool thing is it automatically goes in there. But anyways, that was just kind of like the point of why points instead of strings, or why, you know, why that is. But we can get into what strings actually are. So how strings are described, now that we got like the physics part of it out of the way. Yeah, what's up, Almighty? I see you're using the hand raise emote. While he loads that, what I thought was kind of funny is basically how strings work is, instead of like how we have quarks and protons and neutrons, which are those points that I was talking about, strings vibrate, and how they vibrate is what causes them to appear as points. And I'm air quoting here, but they appear that way. And so the way I kind of thought about it is like, imagine dancing, right? So imagine you're a string and you are dancing. And depending on how you dance, that's a certain style, right? So like, if you were to do, I don't know, breakdancing as an example, like people would know that's breakdancing. They would say that you're a breakdancer, right? Now let's say instead, I want to go and learn like the waltz or something. So, that if someone saw you doing the waltz, well, they would say, oh, well, this person's, you know, classically trained. They're, you know, a classical dancer. And you are both, right? You know both dance forms, but just because the way you're dancing at a certain time, people associate you a certain way. And that's kind of like how strings work. How can you just describe strings or what exists? How can they be different when the side they're at would not behave the same? See, that's what's actually hilarious about this thing. Is because a lot of this is theoretical physics, it's essentially that. They're basically coming up with reasons that things happen. And there's like... It's hard to say why, because we can't really prove that it exists yet. It's kind of like... We know that we have these issues, right? So, because we have these issues of quantum and general relativity not meshing, we need to find a solution that works to mesh these two. And where theoretical physics comes in is that we then just kind of, I don't want to say make things up because it's more like an educated guess of like what goes on, but basically make things up. And yeah, as long as the math works, they run with it. And this is kind of like why I would say that string theory, while it's known, isn't really an accepted form of like physics, like because it doesn't have the meat to it of why. So it's right now is purely theoretical. Like what they do have is just math. Like one of the things we'll talk about here in a minute is something called a gravitron, and a gravitron is air quotes the string or particle that carries gravity. And they were able to use the math that they learned from trying to solve string theory to find the gravitron. And if we found the gravitron, then string theory was... It is very, like, you know, it's very back and forth. Like, there's pieces that make sense with string theory, there's pieces that don't. And it's just a matter of finding the math that works to where we can get it to experimental physics to actually run with it. I hope that made sense. It basically was a really long way of saying... They have no idea it exists until they can prove it, but they can't prove it because they don't know the math for it yet. if that makes sense. It is, yeah. It's definitely bonky. But so to go back to like the string thing, so we have our dance form. You know, where we're either a breakdancer or we're doing the waltz. We get some test other things that we don't know to try and prove is correct. Pretty much, yeah. I mean, like, it's like you know all science, right? You would form a hypothesis based on, you know, your environment. And then you would take the hypothesis and you would put it to a test. And assuming that the test proves that you're true, then you can turn that hypothesis into, you know, results or a theorem. And so it's pretty much... String theory is just at the stage that they can't do... They're formulating the hypothesis. They don't even really know what the full hypothesis is yet. They're just trying to get that nailed down so that they can then take it to those experimental physicists to be like, okay, I know this should happen here. Can you prove it's true? And if they can, great. Well, then we know that we have something that we can work off of that's like a, you know, observable phenomena. But if they can't, well, then now we have to go back to the drawing board and we have to like basically repeat everything, being like, okay, we know that this may not be true. See, this is the critical thing here. May not be true. Just because we were not able to prove it in a singular instance does not mean that it is not true. Especially like things here on Earth, we're limited in scope. Because these strings are so small. They are the Planck constant. So I'll talk about the Planck constant in a minute. They're so incredibly small that to be able to observe them in a meaningful way, we would have to have a microscope that's basically the size of like a planet, if not bigger. Like because their forces are so like weak, we can't even observe how they act. in all this. Except Spinach, however. But so it's purely theoretical. Yeah, with infinite equation. So I already kind of talked about this a little bit. With points, we have problems of like singularity, for example, where like a black hole collapses into a single point of infinite density. That doesn't really jive with the rest of the universe. Believe it or not, infinity is not really... It doesn't really make sense. Like, if you were to go into a black hole, and you were to go to the point of singularity, literally everything we know about physics, gone. It would break down. It would not make sense. And I'll talk about this in a little bit in a later slide, but this is why we have string theory. String theory fixes that singularity. It gets rid of singularity. So I will hold that note because this is only the first slide, but I will hold that note. So I'll hop over here. Something that was kind of interesting about string theory is like, there's a couple items here. So first of all, I didn't know this. Space actually isn't as empty as one might think. So whenever like I was looking into this, so I want you all to think about space. What do you think when you think about space? I'm not talking like planets, I'm not talking stars. I'm talking about the areas that exist between the celestial bodies. What do you think is out there? Without looking at the screen right now. Well, apparently, what is out there... No, actually, I'll give you a second. Hold on. And also, look at my notes while I'm... Vacuum, okay? Okay. So that is one of the things that is out there, is the vacuum of space. There is a type of quantum field. Vacuum is the lowest energy level of the quantum field. I'm on Earth right now, actually. The crash so ended, but sometimes. Radiation, yep. Void, death, depending on if you're prepared or not, but yes. There's also, like, you know, cool planets with a bunch of life and everything, too. And, like, you know, cool explosions, like supernovas and, like, pretty stars, gold, platinum. You guys remember those conversations? There's a planet that rains diamonds sideways. That's really cool. But, so there's also what's out here is what's called a quantum field. And this is kind of where things get really interesting. Is a quantum field, the best way I can think to describe this, is like the fabric of reality. So if particles play on that fabric and move along that fabric, this is the fabric that they move on. It is quantum fields. And what's really weird about these things, right? Okay, I hope you guys can hear the Spotify, because literally as I'm talking about this, the Interstellar song just started playing, and we're probably going to get muted, so everyone just enjoy the ride while we can. But, the quantum fields, so what's interesting about these things is that where it would appear there to be nothing, right? It is blank. You could go out there and you could, like, fly out there, but there's nothing there. There's nothing seemingly there. There's no matter there. Its keyword is there's no matter there, right? However, there is the quantum field. And the quantum field exists everywhere. Everything that ever is has a quantum field because it's in the fabric of reality. And what's really interesting is that there's these things called virtual particles. A virtual particle is something that exists in our reality. So we're going to start to talk about dimensions now. I'm banning the word string right now. Well, see, I already outthought that, because if you look at the key text under the ban of strings and banning my voice, I said unless it's during Galactic Curiosity, in which this is disabled. So ha ha ha. I won't honor this until the Galactic Curiosity is disabled, or until it's over. Yeah, I saw that coming. I already saw it. I got that 2000 IQ brain. But, so the virtual particles. Basically what that is math saying that two particles can spontaneously come into existence at the same time under the assumption that they will immediately cancel themselves out. So, At any given point, I mean, literally, right now, right in front of you, there could be two particles that burst into existence, and within, I mean, literally, no time at all, they would hit each other and cancel themselves out. And this is going on everywhere, all at once, all the time. And so this is the quantum field. And as a little aside here, this is also where Hawking radiation comes from. So what happens there with Hawking radiation is saying that if this happens near a black hole, the black hole's pull is so strong and so quick that one of those two particles could actually fall into the black hole, which would leave the other particle stranded in space, and it can't be deleted by the other one. That's Hawking radiation. So I just thought that was kind of cool. The strings themselves that like kind of go through our reality can either be open or closed, and depending on what they are, if they're open or closed, it like depends what they can do. It depends on how they can vibrate and what they can become. So one example is if you have like, imagine you have a jump rope and imagine you have a hula hoop, right? But where does the matter come from? If you're talking about the virtual particles, another dimension. So this is like the thing that gets really wacky with string theory, is that there are, with the formulas, there are 11 dimensions. So we have, you know, our first three, so up to 3D, which is the world we live in. Then there's the fourth dimension, which is time. And then the fifth dimension through the 10th dimension are used in most of the different string theory, like, what are these called? Hold on, I want to skip ahead. Too far. String theory variants. So there are 10 dimensions used in pretty much all of these, except for the last one. The last one uses 11. But we'll get to that when we get to that. So I'll go back here. So yes, dimensional contact is huge in string theory. So what we see and what we perceive now isn't necessarily everything. There's gonna be things that can come into our dimension or leave our dimension based on how the string is connected. And we'll get into it with like branes and everything too. So one of the things I was gonna say with like the shape of the noodles is that if you have like a hoop, right? The hoop is saying that this is a string that is free floating. It is not connected to anything. It is just flying throughout space. And these are your weaker connections. These are your weaker forces. Specifically, this is the gravitational, the gravitron that is being made by these loops. And the gravitron is an extremely weak force. Now, if we look at the noodles, or the jump rope and the example I gave, those are going to be your star forces. Those are going to be your nuclear forces. Those are going to be your electromagnetic forces. And those are attached to what's called brane. And I think I'll get into brane in the next slide, yes. So, those are attached to what's called a brane, which is kind of like an anchor point for them. But yeah, we'll hold on to that for a second. We'll hold on to that. And anyways, based on how those vibrate is how they turn into like protons, neutrons, electrons, what have you. So just kind of some like other info, and I don't want to like go too into everything because there is obviously quite a lot of detail here. Not so much in like the slide, but just like in what goes on. So if there's something that maybe I don't explain too well, you may have questions later, definitely feel free to reach out. You know, I'm always open to talking about this stuff and like doing research for you guys. So if there's something you're interested in, definitely let me know. So let's see, what else do we have on here? So I already mentioned the extra dimensions. That one's behind me. The clustering vibrations, I mentioned gravitron, so we're good there. The other thing is that the Planck length. So that is the smallest meaningful scale that this acts upon. And the Planck length is what they believe to be the length of the strings. And the reason for this is if the strings were any smaller than the Planck length, then they wouldn't have a meaningful impact on the world we're in, like whatsoever. So whenever I was doing research, I was looking into this, it was like, I was like, I didn't understand this. This didn't make sense to me. How can something be so small that it doesn't have an impact? Because the way I thought about it is like, imagine dominoes. Have you guys ever seen those dominoes things where they start with like the really little domino and then it like cascades until it's like literally knocking down buildings kind of thing? Luckily, I was thinking about it. I was like, well, you know, something small could have a huge impact on the actual world. And so then I was like looking into it, and it turns out, I want you to imagine that same situation, same domino situation. These things are so small that you literally would roll right under your domino. Like the first domino, the smallest domino you can get, you would roll right under it, like between the space of the domino and the floor. That's how small it is. It is... If it was a part of the plank length, that is. If it was a part of the plank length, you would just roll under that domino. It would have no impact. And I was like, that is crazy. Like, there is things that small that... Anyway, that's nuts. So we know it can't be that small. Because we see, like... We believe, I should say, we believe we see things in our reality, such as, like, black holes and everything. It also cannot be bigger than the Planck length. Because if it's bigger than that, whenever we're doing our, what's that called? The particle collider, or the particle accelerator, whenever we're smashing particles together, if the, it's the string theory, if the strings in the string theory were bigger than the Planck length, then we would see some sort of standard deviation with those, with the crashes, with the collisions, and we don't. So, it is believed to be the size of the Planck length. That is, again, not a proven thing, purely hypothetical, purely theoretical, but that is where they believe the size to be. So I've mentioned this a few times now. So branes. Branes is where things get weird. Really, really, really weird. Branes are basically multi-dimensional membranes in the sense that, like, I think this has a better image of it over here. So, on the left image there, the black boxes that you see are branes, and then the strings that go between them are the strings of the string theory. So, branes essentially act as contact points for the strings as they go through, you know, the different dimensions, our universe and everything. And depending on how the brain fluctuates and how it moves, is how the strings receive their vibrations and how they, you know, they do their thing. So, there are a lot of theories with these things. I mean, it literally goes from, you know, people believing that branes are... Our universe, our entire universe is a 3D brain on a higher dimension. There are theories that this is the multiverse. Like, these things could be so massive and, like, mess with so much stuff that it could be multiversal, like, just by almost default. And, yeah, it's absolutely nuts. And what's even more so is that, well, there's actually a theory for the Big Bang involving branes. Is if we have two potential universes, and they come into contact, like, dimensionally, that is, like, imagine you have, like, a bunch of strings everywhere. They're all ready to go. They're loose and ready to go, and they smash it together really quickly with something else. Those strings are gonna go crazy. So, by exciting all of those strings, you're now, you know, bringing all these things into creation, which is kind of like what's going on here. So, these two fabrics here, you can't see my cursor, but just imagine that it's in the center there, where it says Big Bang with an X. These two fabrics touched, and that caused the excitations to go through all the strings that make up our universe, and that caused the Big Bang to start. So that is one of the theories of how the Big Bang, how it started. The other thing is that if these are true, why is it doing cowboy music now? What the heck? This is also like, branes would be kind of skipping down to the heat death portion of this that Waylord is currently covering. Is literally cowboy and let's go. But if these are true, and I don't know if you guys know, do you guys know about entropy? Like how the universe is supposed to end? See you, space cowboy, yes. But basically how the universe is supposed to end is that everything that is will eventually fall into a black hole. And that black hole will fall into other black holes. And well, technically, there at the end of it all, there should be either multiple black holes that slowly fade away, or one literally like colossal black hole that will also fade away. And the thing is, as energy leaves the universe or this dimension, everything will slow down to basically a stop. They won't necessarily disappear like that. The information will still be there because you can't delete information, but it won't be able to move because there's no outside energy acting on the system. So if branes are true, that means that we could then take these fabrics, or, you know, not so much we, because that is like, that's levels approaching divine, if not like already divine. But you would take these fabrics and you could hit them, and by doing that, you could literally rebirth a universe. Because that would excite all the strings that exist within everything. And then we would have that outside energy again, and boom. We would be back in business. Now, one thing that did mention here, that I kind of skipped over for a second, was the black holes, string smooth singularity math. What that is saying is, I don't know if you guys have seen it recently, but there was the discussion about that we could live that our universe may exist in a black hole. And so I was looking to, I was like, well, you know, if there's strings, does that mess up that theory? Like, it, you know, does it play? And it does. It actually works with the theory of that we live in a black hole. Because what it's saying is that singularities are a problem for string theory, or really physics in general, because you can't have an infinite point. It just doesn't make sense. And so what string theory is saying is that as information goes into a black hole, what could be happening is that information... Okay, now we're doing frickin'... What is this? The Duel of the Fates? You're done. You're done. You're done. We're putting that away. This is supposed to be on big brain music. Oh, yeah, we got like a 6-shooter, and now we're going with the, I'm about to bust out the lightsaber kind of thing. I'm sorry. Okay, here. I'll put it back on. You can have it. It's space related. I'll give it to you. Give it back. It's back. It's back. You're good. Oh, that completely threw me off. Now I'm just thinking about the fight with Darth Maul and everything. Black holes. Oh, yeah. So if information were to fall into a black hole, right? Instead of just being essentially deleted, what would be happening is that information is being encoded upon strings that exist in that black hole. And if strings exist in that black hole, the way you could kind of look at it is like, imagine like a USB stick, right? Is instead of information is being lost, you're essentially storing it on something that exists in that black hole. And if the dimensions were to hit each other, it would bump and could create a universe. Or even, maybe that's how it is now, is that black hole is like touching another another brain, and it, whatever that information goes in, it just creates another universe. It's here, it's just really quiet. It's like doing like the setup. Yeah. It's coming back, don't you worry. Quick aside. If everyone had a lightsaber color, what lightsaber color would you have? Mine would be either purple, or I really like the orange ones, I'm not gonna lie. Red. I couldn't be a Jedi. Oh wow. Okay. You know, I appreciate the honesty. The no attachments, like that might depend on when, like, what year you are a Jedi, right? I think that was like, wasn't it High Republic that they didn't like the attachment thing? I don't think that was all the time, because like Qui-Gon Jinn didn't follow that edict. Like, he actually, if Qui-Gon would have been Anakin's master instead of Obi-Wan Kenobi, then it probably would have been okay, because Qui-Gon actually supported the attachment thing, because it like generates love. Give me Darth Maul with the robo legs, literally. Not like, also Darth Revan. Like, don't get me started on that. I love Star Wars is peak. Yeah, it's alright. So let me go ahead and skip over through here, because I just kind of wanted to mention the singularity thing with all the universes. So we do have a couple of ways that we can prove string theory. So far, none of these have necessarily been found, but this is what's being tested, or what's being trying to be found. So the first is extra mentions. If we can prove that something basically translocates into another step higher, like another dimension, then we know that there is string theory in some form. We don't necessarily know the direct answer, but we know that there are other dimensions that information can pass between. Basically, how we're doing this is we're taking two particles in a particle accelerator and slamming them into each other. And as we're watching it, if we see any energy at all disappear in a way that we don't understand, then that is almost certainly inferring the fact that there is cross-dimensional travel, essentially. That's the first way. The other way is that if we do discover that gravitron, that would be huge for string theory. Huge. Because that means at least that the second and third theorems are right, I believe. Because they talk about having the closed loop system. So if everyone remembers the hula hoop, the gravitron is the hula hoop. So that would be a huge step. But like I said before, if to actually be able to find a gravitron, because they're so weak, it would take just a massive sensor of some form, some sort of detector that'd be just gargantuan. Planet size is literally just like a back of a napkin kind of calculation. It could be bigger. It could be genuinely massive. The other way is there is what's called a cosmic string. So cosmic strings were around during the very beginning days, or the early universe, where things were still, quite powerful. And what a cosmic string is it is literally a one-dimensional line that is so incredibly dense that it is like an insane level of density. It'll actually cause gravitational lensing to happen whenever you're looking at stars. So that kind of GIF I have above there is an example of gravitational lensing. Is just whenever a star should be in a certain position, but due to some sort of hyperdense object, the light actually gets bent around that object such that it appears in a different position. We see this a lot with like black holes. It's a good example. But like anything that's heavy like that will cause it. I also know this song and I cannot think of it right now. So there are a couple different string theories. There are 5, I want to say. Yes, 5. So there's type 1. Type 1 is talking about having both jump ropes and hula hoops for the strings that we have available. The type 2 takes away the open string and says it's only hula hoops the whole way down. But depending on how they are oriented in space, they could behave different ways. Then we have the mixed symmetry, so this is a little bit of everything here. Which I have a lot of notes on, but yeah, it gets spicy. Type 1 is where your pancreas doesn't work. Oh. And then we also have M theory, so this is the one to unite them all. M theory was literally made to... The problem is, each of these ones here, they have stuff that works, but they do not work together. It is very, 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 very difficult to get these to work together, and there's like a huge contention over which of these is correct. And the thing with most of these is they operate on scales of like, I want to say 7 to... No, that's not right. 9 to 10 dimensions. And then M theory is whenever you have the 11th dimension. So what this is saying is that there's 10 dimensions in total, plus time. So time is treated as its own dimension, so we get 11 in total is where that comes from. But, yeah, does anyone have any questions? I'm sure I kind of skipped around a little bit there. Just make sure I covered everything. I got distracted. As soon as time becomes involved, my brain starts forget. Time is so cool. Literally, time is so cool. Like, if you get into, like, time dilation, or, like, traveling at the speed of light, or, like, I don't know, just, like, all this stuff, it's so interesting. It becomes so interesting. And, like, whenever you, like, look at some quantum stuff, like, time crystals, where they literally take moments in time. Oh, so it's wild. It's crazy. Let me see. I did have a couple of notes here, so let me go ahead and look at these. So, pull this up. If I pendulation, I don't know. I think it's real. It would be so cool because that's something that is like you could actually test that. Because well, you could theoretically test it. I don't know if you could test it on Earth because it would require something that's just so dense that it would throw things off. But technically speaking, if we ever found like a hyperdense body, you could definitely test it, and I think that's really interesting. Relativity, or time being relative. There we go. Is definitely real. Pretty sure. I've experienced that one myself. So let me go here and go over some of the things I might have. So we covered that. Link length. Yep. Hit. I thought this was kind of funny though. So open strings are like kind of like space spaghetti. So they can dangle, attach to stuff like the branes and everything, or get attached. Or I already said get attached. Closed strings are like space donuts. Self-contained, delicious lips that roll around, carrying gravity wherever they go. I thought that was a cute little example. One of the things I did look into was like, so I don't know if anyone's messed with. So whenever I was talking about dimensions, you know how I was saying like we have 3D, which is like the world we live in, and the fourth dimension is time. One of the things that I ran into that I was like kind of confused on is like, well, wait a minute. I've seen a four-dimensional, like I've seen a tesseract. And so I was like, now how's that work? Is a tesseract the same fourth dimension as like what they're talking about with string theory? No, it's not. A tesseract is what's called a spatial dimension. Whereas what they're messing with is just a like physical dimension or something like that. So the way that I kind of built out like an example is like, imagine if reality is like a giant cosmic layer cake, right? We live on the top, the frosting, which is like our third dimension, and we have time. We can move around the cake, we can see it, we can like look down, 3D, the whole 9 yards. Now we have a tesseract. A tesseract is kind of like saying, hey, what if there's another flat layer above us, but we can see we can see it. We can see its shadow is how you describe it, but you can't actually get onto that layer because you can't move your body in a way that gets you onto that layer of cake. It doesn't make sense. You can see its shadow, you can actually like physically see what it kind of is, but you can't really see what it truly is. So string theory is different. The way it's described with third dimensions is there's no other layers. There's no extra room to move around in. There's, nothing like that. It's more so what the cake is made out of. So the cake is like how long it was baked for, what the temperature was, what the flavor is, if there's sprinkles, things like that make up our cake. That is the string theory dimensions. So I hope that helps that explain it a bit more, like between spatial and like actual dimensions. But I just thought that was kind of cute too. So, there was one other thing I had. I actually have some questions for you guys. So, what else in space would you like to uncover? Is there anything that you're interested in? It doesn't necessarily have to be like galactic levels of stuff, but if there was anything that you would like to see talked about or like looked into, what would it be? If you could prove or disprove string theory, what experiment would you design to do so? And I think that's about it. The next topic I am going to go ahead and announce now, so we get a little bit of a ahead of schedule. So next week, because we talked about strings today, I thought it would be kind of fun if we talked about music next. So we're going to go from the music of the universe to the music of Earth. So that is going to be the next big Galactic Curiosity. Is going to be music. And yeah,